Hello and welcome to the pre-lab video series for York College, Pennsylvania's General Chemistry 1 sequence. Today we're going to consider the gravimetric analysis for phosphorus exercise, part of the Chem 1 sequence. The goal of this exercise is going to be to determine the mass percent of phosphorus in a sample of fertilizer. There are, of course, a number of other nutrients used for different types of plants in various fertilizers, but we've chosen to try to analyze phosphorus content in a fertilizer. The word gravimetric in the title Gravimetric Analysis means by mass. So what we're going to do in this exercise is essentially take a pile of fertilizer which contains a number of things, perhaps phosphorus, nitrogen, maybe some other nutrients like calcium that plants and the soil might need. And we literally want to extract or pull out the phosphorus from this pile and put it into a different compound over here. In this second compound, we'll know very carefully the formula of the phosphorus. It will not be only phosphorus, it'll be part of this other compound. We are unable to just extract the pure phosphorus and weigh how much phosphorus was in the sample. So we'll have to do a little bit of stoichiometry to relate the content of phosphorus in our new compound that we formed, and thus determine how much phosphorus was in our original sample. The procedure itself will be fairly straightforward. You'll dissolve a sample of fertilizer. Most of the fertilizer will dissolve, however, some of it will be insoluble, and so you'll have to filter out the insoluble contents of the fertilizer first. Among the chemicals that dissolve then and go into solution, you can conduct a reaction between ammonium hydroxide and form a precipitate that contains your phosphorus. And so the formula of this precipitate is MgNH4PO4. And so all of the phosphorus that was originally in our fertilizer will be converted into this compound, this magnesium ammonium phosphate compound. And we can then precipitate this, or it will be precipitated, and we can filter it out of solution. So if you haven't yet filtered anything this semester, you're going to use an apparatus that looks like this. This is your Buchner funnel. The top part of this is a Buchner funnel, the white porcelain funnel. This is mounted atop what we call a filter vac, this black rubber ring to create a seal, to an Erlenmeyer flask that has a side arm on it. This goes in one of the fume hoods, to which it can be connected, of course, to the vacuum apparatuses at the back of your fume hoods. Notice that I've clamped this in very tightly so that it doesn't fall over. The rubber hose that you would connect to the side arm will want to torque or twist the flask, so be sure that you're using the proper precautions to keep the apparatus nice and secure. Once you recover this filtrate through your filter system on a piece of filter paper, you'll need to dry it. And so you need to take special care in making sure that you follow the procedure carefully today. You will need to weigh your piece of filter paper, because once our magnesium ammonium phosphate is on the filter paper, we won't be able to separate it from the filter paper. And so we can weigh the combined product plus paper at the end of the lab after it has been dried in the oven. Now we'll dry this on a watch glass. So a watch glass is the sort of slightly curved piece of glass that you can find in your chemical, among your equipment, I should say, in your drawer. And so you can place your filter paper with product on it into the oven. to dry. This will be hot when you take it out of the oven, of course, so take the appropriate precautions to get your sample out of the oven. Make sure you label your particular watch glass. Everyone's watch glass will look essentially the same, and so you'll need to put a piece of tape onto your watch glass, and you can even weigh the watch glass before you put it into the oven, and then afterwards you'd be able to weigh the entire watch glass filter paper product combination and subtract the various masses to come up with finally the mass of the product that you're interested in. Okay. And it'll be that mass of product that will allow you to determine the mass of phosphorus that was in it, and then ultimately relate that back to the mass of phosphorus in the fertilizer. So the procedure itself is fairly straightforward, and I'd rather focus on the calculations involved in the pre-lab because they are very closely related to the calculations that you'll do as part of the lab report. So let's look at the pre-lab questions then, and determine the mass percent of nitrogen in ammonium hydroxide. So we've worked with mass percentages in chapter 3 of our textbook in chemistry. And so ammonium hydroxide is NH4 and OH. And so the percentage of nitrogen in this would be found by taking the mass of nitrogen divided by the mass of NH4OH times by 100%. Now we don't have any actual masses of compound. We haven't been told any particular masses. But the ratio of nitrogen to ammonium hydroxide would come from the molar masses. Every 1 mole of ammonium hydroxide, which would have a total mass of 35.05 grams, would contain 1 mole of nitrogen, whose mass would be 14.01 grams. So we can not invent, but we can use the mole relationships to generate the masses that we would need to have our percent composition, our percent mass. So this comes out to 40.0% nitrogen in this case. You'll want to conduct an equivalent version of this in your calculations, and it's actually part of pre-lab question 2 for our magnesium ammonium phosphate compound. So let's look at that one. In part 2, this is really duplicating what we're going to do in the lab today. 10 grams of plant food is proposed to be analyzed. We produce a precipitate that takes all the phosphorus out of the plant food and incorporates it into our MgNH4PO4. What is the percentage of phosphate in the original plant food sample? Okay. So we took our phosphorus and put it into MgNH4PO4. This compound has a molar mass or molar weight of 137.322 grams by adding up the magnesium, the nitrogen, 4 hydrogens, phosphorus, and 4 oxygens. So let's calculate the percentage of phosphorus just as we did for nitrogen in our first example. There's only 1 mole of phosphorus, which would weigh 30.97 grams of phosphorus, divided by this entire mass of 137.322 grams. So phosphorus accounts for 22.55% of the entire mass of magnesium ammonium phosphate. So while we calculated this on a mole, scale, we now can interpret any sample of magnesium ammonium phosphate. 22.55% of its weight comes from phosphorus. So if we had 1 gram, we would have 0.2255 grams of phosphorus. If we had 1,000 grams, we would have 225.5 grams of phosphorus in that 1,000 grams of sample. Okay. So how can we use this? Well, our compound that we produced, we collected 5.72 grams of the magnesium ammonium phosphate, we're told. Okay. Of this, we now know that 22.55% is phosphorus. So when we multiply by 0.2255, we're determining the percentage or the mass that is actually phosphorus. 1.290 grams of phosphorus are in this actual 5.7 grams of magnesium ammonium phosphate. So to determine the percentage then that phosphorus accounted for in the original fertilizer, that would be the 1.29 grams of phosphorus divided by the 10 gram sample of the plant food or fertilizer, and then multiplying by 100%, you would come up with a 12.9% phosphorus in the plant food. So in a nutshell, that's what you'll be doing in lab today. You'll be collecting magnesium ammonium phosphate, and now that we've already determined the percentage that phosphorus accounts for in that compound, you simply need to take the weight of your sample of magnesium ammonium phosphate times by this 22.55%, and that will tell you how much phosphorus you have. Now, the phosphorus in the plant food is not actually in the form of elemental phosphorus. It typically comes in the form of diphosphorus pentoxide, P2O5. So you'll have one more step where you'll need to figure out how much P2O5 contains that amount of phosphorus. And our third pre-lab question asks us to essentially do that. Okay? So we have, if all of the phosphorus in a 3 gram sample of MgNH4PO4, okay, is extracted and used to make the diphosphorus pentoxide, what mass can be produced? So what mass should we expect? So this is a stoichiometry problem, really. We're going to convert our grams of MgNH4PO4 to moles by dividing by the molar mass, same molar mass we had above. Now, each mole of MgNH4PO4 contains 1 mole of phosphorus. And then it takes 2 moles of phosphorus to make 1 mole of P2O5. And then lastly, each mole of P2O5 would have a molar mass of 141.94 grams. So when we take our 3 divided by 137.322 times 1 divided by 2 times the 141.94, we should be able to get 1.55 grams of P2O5. Now, to relate this to what you're doing in lab today, you're going to be, again, extracting magnesium ammonium phosphate, or generating and collecting magnesium ammonium phosphate. And the amount of phosphorus that you have in your magnesium ammonium phosphate originated as P2O5. So you could begin not quite doing this last calculation like this, but as part of your calculations in the lab, you're more likely to need to take the amount of the phosphorus that you generate and turn it into P2O5. And that would begin more with the grams of phosphorus, say from up here, okay, in this step, times then converting the grams to moles. So a mole of phosphorus, 30.97 grams. And then you would have, beginning with this step here, you would go 2 over 1, okay? And then the last step would be the same. So that's a little peek at some of the calculations that you would need to do. And ultimately, you'll take your mass of P2O5 divided by the mass of your fertilizer or plant food sample that you begin with. Because again, we're not, the plant food label, if you read it carefully, tells you that you do not have just elemental phosphorus in it, but that rather the phosphorus is expressed or provided to plants in the form of P2O5. And so if we want to compare, we need an apples to apples comparison where we have to calculate the amount of P2O5 that we originally had in our sample of food. Okay? Should be a very interesting experiment. You're going to take, again, one compound and just dissolve it completely. You'll see it disappear. And then when you're done, you'll have a completely different compound, this magnesium ammonium phosphate, from which you can backtrack and determine exactly how much of the phosphorus you began with. So I hope you'll enjoy this experiment and that you get a great result. Have a good day.